Hello students. So I want to talk a little more about the Sterling numbers now that we're done with the 12-fold way. And I guess what it would be helpful to have is some sort of a formula for them. So let's try to think for a little bit. Suppose I know what a Sterling number is and I want to maybe find the next one. Now you might say, okay, well we have two parameters here. We have both Sn and we have n and k because we've defined our Sterling numbers to be the number of ways that we can partition a set of n objects into k, exactly k, subsets, non-empty subsets. Okay, so for example, suppose I know what my Sterling numbers are when n is equal to 3, and I want to figure out what the Sterling numbers are for when n is equal to 4. Like, let's say I want to find Sn for 3. So basically, we'll assume that I know all the Sterling numbers when n is 3. And now I want to know what happens when I toss in the next block. So let's say I know what happens for red, orange, and yellow, and I want to toss in that green block over there. Okay. So what is this going to count? This is going to count the total number of ways that I can split these 4 objects into 3 unlabeled subsets. Okay, so one thing I could do is I could put the green block by itself, and then I have to split the remaining blocks into 2 subsets. So now there's only one way I could put the green block by itself. So what I'd have is I'd have 1 times, okay, how many ways could I split the 3 remaining elements into 2 subsets? Because I want 3 total, and one of them is going to be taken up by the green. So that's going to be S3, 2. But there's also another possibility. The other possibility is that green is not by itself. Okay, so now I have to think about this. So what'll happen is I need to know how I can add green to the existing subsets if I break up these 3. Now how many subsets do I need? Well, I need a total of 3 subsets, and green's getting included in one. So basically I need S3, 3. But then I have to choose which subset I'm going to be placing green in. And how many different possibilities are there going to be for these subsets? By the way, these subsets are totally distinguishable because they have different distinguishable elements in them. So how many different possibilities am I going to have? Well, 1, 2, 3. So it's going to be, I like to write the 3 in the front. It doesn't matter, but plus 3, S3, 3. Okay, so let's do another example. Let's say I have, I know what the Sterling numbers are when n is equal to 5, and I want to toss in a 6th element. Okay, so let's say I want to find I'll stick with 3, S6, 3. Okay, so one more time, either I put this new block, the 6th block, the purple block, which looks kind of black, by itself. Okay, there's only one way I could do that. And then I have, well, one subset's already taken up. So for the other 5, I have to split them up into 2 subsets, and I can do that in S5 2 ways. Okay, but now I have to deal with the possibility that this block is not by itself. So I have to include it into an existing subset. Now, I have 5 blocks and I want to make them into 3 subsets, so that's going to be S5, 3. Now, I have to choose, and this is just one possibility of many, that's one way I could do it. I have to choose a place for this block here. So how many ways could I choose a place for this block here? Well, I have, is it n different possibilities? No, I don't have 5 possibilities. I have 3 possibilities because the number of possibilities equals the number of subsets. So that means I'm going to have 3 again right there. Okay, so now let's try and do this in general. Suppose I want a formula for Sn, k. Okay, now, or let's do n plus 1. Make it even easier for us to talk about this instead of having to talk about things in n minus 1. So I already know, let's say, all the Sterling numbers for Sn, k, for all possible values of k. And now I want to find out what Sn plus 1 of k is for some k. Okay, so I now have an n plus 1th object. And if I leave that object all by itself, which could only be done in one way, I'm going to get 1. I'm not going to bother to write the 1. But what happens? Well, I have to divide the remaining n into how many subsets? Well, k minus 1 subsets. And I have another possibility, and that's that the n plus 1th object, isn't by itself. In that case, I need k total subsets, so I'm going to have to split the n remaining elements into k total subsets, and then I have to choose where this n plus 1th element goes, the n plus 1st element goes. And how many choices do I have? Well, that's going to be equal to the number of subsets, which is k. So that is a formula for the Sterling numbers. And of course, I said we have another notation for this as well, which we can say n plus 1 Sterling k. It's not proper notation, but it sounds like n choose k. It's good enough for us secretly. So n Sterling k plus k minus 1 plus k times n Sterling k. And we can use this to find Sterling numbers from existing Sterling numbers. So, for example, let's say we wanted to take, I don't know, a very simple example was the Sterling numbers with 2 objects. So it's really quick for us to compute S21, which is the number of ways I could split 2 objects into one subset. Well, that's only 1. And then S22, that's the number of ways I could split 2 objects into 2 subsets. Well, that's only 1, okay? But from these 2 numbers, I can now get, let's say, S31, because using our formula here, it's going to tell me, okay, S31 is going to be equal to S20, not possible, plus, now my k here is 1 times S2, 1. So that's going to be 1. For S32, it's going to tell me that I get well, what do I have? I have S2, 1, I subtract 1 from each, plus, then I take my k, which is 2, times, then I just subtract 1 from the 3. So S2, 2, which I know this is 1, and I know this is 1, so this is 1 plus 2 equals 3. And we can quickly check that. If I have 3 objects, and I want to know the number of ways I could split them up into 2 subsets, well, that is 3, because I could do this. I could leave the red by itself, I could leave the yellow by itself, or I could leave the orange by itself. And then for a last example, S33, well, that's going to be equal to S22. I subtract from each of them first, and then plus 3 times S. Okay, now I just subtract from the n. So that's going to be 2, 3. But notice something. It's going to be impossible for me to split 2 objects up into 3 sets. So that goes away. So what do I have? I just have S22, which is 1. And what this is telling me is that the number of ways I can split 3 objects into 3 sets is only 1, which is correct. Remember, the sets are not distinguishable. So as you can see, we can compute existing numbers from previous Sterling numbers, and we could find any Sterling number that we need in this fashion. By the way, everything we're talking about is for Sterling numbers of the second kind, which is the only kind that we've introduced, which is why I'm just using the word Sterling number for everything.